Moving on in our transformations unit, today we're going to talk about symmetry. We're going to talk about two different types of symmetry, line symmetry and point symmetry. Line symmetry has to do with reflections and point symmetry has to do with rotations. And they're two different things. We are first going to look at line or reflectional symmetry. Line symmetry would mean it looks exactly the same after being reflected over a line. So that would mean you can use a line to reflect the shape and it looks exactly the same. How many lines of symmetry does each hexagon appear to have? So let's see if we can draw a line that would be like a mirror and it looks exactly the same on both sides. Okay, obviously this line is not a line of symmetry because it does not look exactly the same. However, if I draw a line right here, I can see that this shape and this shape are exactly the same. It looks like it has been reflected in a mirror. It's like a mirror image. Are there any other lines of reflection? Yes, if I could draw a line right here and see that it's exactly the same on both sides. Okay, anything else? No, those are the only two lines of reflection. Let's see if we can figure out lines of reflection for this hexagon. I can see I can draw this line right here, and that makes the shape the same on both sides, as well as this line right here makes it the same on both sides. Okay, let's see which other ones we can draw. If I draw this corner from corner to corner, it is the same on both sides. Okay. Also from corner to corner here, it is symmetrical perfectly around that. I can also draw connecting the middle here. That is a lot of lines of symmetry. There's 1, 2, 3, 4, 5, 6 lines of symmetry. Notice that a hexagon, which has 6 sides, has 6 lines of symmetry. This is what's called a regular hexagon, which means all of the sides are congruent. So since there's 6 congruent sides, there are 6 lines of symmetry. And let's find some lines of symmetry for this shape. There's not a line of symmetry here. Okay, not a line of symmetry here. How many lines of symmetry do you see? There is one line of symmetry for this shape that acts like a mirror so that this side of the line and this side of the line are exactly the same but reflected. You've probably looked at lines of symmetry before, so hopefully this isn't too unfamiliar to you. Let's look at our regular polygon. So like I said, when this hexagon, which has 6 sides, had 6 lines of symmetry. Regular polygons are polygons with all congruent sides. An equilateral triangle has all congruent sides. And then these are the other names of the shapes that you need to know. Let's see if they have the same amount of lines of symmetry as number of sides. An equilateral triangle. Let's see, if I draw a line here, it is symmetrical, about symmetrical. I could also draw from this corner to the middle, and it would be the same on both sides, and this corner to the middle. So there's 1, 2, 3 lines of symmetry. Are there any others that you can think of? No, there's not any others. So that means that there are 3 lines of symmetry for this equilateral triangle. We already said that a regular hexagon had 6 lines of symmetry. Let's look at a square. How many lines of symmetry are there for a square, which is a regular polygon? It has 4 sides. Okay, if I cut a square in half through the middle, that is symmetrical. It's also symmetrical going this way. Okay, are there any other lines of symmetry? Yes, I could connect the corners, and that would give me two triangles that are exactly the same. And any other lines of symmetry? No. So this square has 1, 2, 3, 4 lines of symmetry. So do you think that all of our regular polygons are going to have the same number of lines of symmetry as numbers of sides? Yes, that is the case. So how many ever sides there are is the number of lines of symmetry that the shape will have. Okay, that's the rule, is that it will have the same number of lines of symmetry as numbers of sides. Now let's take a look on the coordinate plane. It's important that you know your equations of lines, which is why we spend a little bit of time at the beginning reviewing our equations of lines. It's important that you know your horizontal and vertical lines especially. This is back in the first section here. So it's very important that you know that x equals a number is a vertical line. Y equals a number is a horizontal line. You need to know your positive and negative slopes as well. So let's take a look at this example. Which gives a line or lines of symmetry? This is why you need to know your lines. What does the line y equals x look like? Y equals x has a positive slope, so it's going in the positive direction, a slope of 1 that passes through the origin. Does the trapezoid reflect across that line and look exactly the same? No. Okay. What is the line x equals 4? X equals 4 is going to be a vertical line because we go to the x-axis to 4 and draw a vertical line. Does that look like a line of symmetry? Yes, it does. It looks the exact same on both sides. However, this one has a second one with x equals 4. So let's see if there is another line of symmetry. X equals 4 and y equals 2. What does the line y equals 2 look like? Y equals 2 would be this line right here. Okay, and does that split it completely in half? No, those aren't the same. X equals 0 and y equals 0 would be the axes, and that is not reflectional symmetry. So again, it is very important that you know your lines, that you know your horizontal and vertical lines, and positive and negative slope lines. Let's do some more. Which line would cause this figure to have the same vertices as the original? So in other words, if we reflected this shape over which one of these lines, would it be the same as the original? See if you can figure out what that would be. Y equals 6 means I would go to the y-axis to 6. And that does look like a line of symmetry. If I reflected, it would be exactly the same. X equals 6 means I would go to the x-axis to 6 and draw a vertical line. If I reflected that, it would not be at the same place. Okay, neither would y equals 4 or x equals 4. So that's why that one was y equals 6. All right, let's find the equation of the line of symmetry for this figure. X equals 0. That means we would go to the x-axis, and would we have a horizontal or vertical line? We would have a vertical line, so x equals 0 would be this line right here. This is the point 0, 1, 0, 2, 0, 3, 0, 9.2. Everything on this line has a y, x equal to 0. Okay, does that look like this figure is perfectly symmetrical about this line? No, it's not. Y equals 0 means we would go to the y-axis to 0 and draw a horizontal line. This is the point 0, 1, 0, 2, 0, 6, 0, 8, 0. Everywhere on this line has a y coordinate of 0. And does that look like a line of symmetry? No, it does not. Y equals x. It's important that you know which ones are positive and which ones are your negative slopes. Positive goes this way, negative goes in this direction. Y equals x would be this line right here. And does this have symmetry about that line? Yes, it does. Y equals negative x goes in the negative direction. That's where all of the y's are equal to the negative x. Does this line have symmetry? No, it does not. Which triangle is symmetrical about the line y equals 2? Y equals 2 is what kind of line? That is a horizontal line. So I would go to the y-axis to 2 and draw the line y equals 2 and figure out which one is symmetrical. And that was obviously this one right here was symmetrical across y equals 2. Now we're going to move on and talk about rotational symmetry or point symmetry. Rotational symmetry means it looks exactly the same after being rotated less than 360 degrees. Now, pretty much all shapes are going to be symmetrical if you rotate them 360 degrees. No matter what shape it is, it will always be symmetrical if you rotate it 360 degrees all the way around. Okay, but point symmetry means it could be rotated less than 360 degrees and be symmetrical or congruent to itself or mapped onto itself. So let's look at these examples and see if these have point symmetry. Looking at this hexagon right here, I'm going to start with this coordinate on 0 degrees and I'm going to rotate it. Okay, I'm going to keep rotating it. At 20 degrees, it's not back onto itself. Okay, but how can I make it back onto itself? If I go over to 180 degrees, it is mapped onto itself. So, does this have rotational symmetry? Can it go back on top of itself if it's rotated less than 360 degrees? Yes, this has rotational symmetry because it can go back onto itself at 180 degrees, which is less than 360. Let's look at this regular hexagon and see if we can rotate it onto itself. So let's pay attention to this point that's at 0, okay? And we're going to rotate it. If I rotate it, this point was at 0. If I move it over to 60, notice that it is back on itself. And then if I move that same point over to 120, it is back on top of itself. So it is symmetrical. And how many different ways can I make it symmetrical? You can make it symmetrical if you move any of the corners on top of each other, and there are 6 corners. That means that there are 6 different ways, 6 different rotations that could make this symmetrical for the first 360 degrees. Okay, let's look at this triangle. Does this triangle have rotational symmetry? Let's see, if I rotate it, okay, if I take this shape and I rotate it, and let's see if it will go back onto itself without going all the way around. It will not. So this will only go back onto itself for 360 degrees. This shape does not have rotational symmetry or point symmetry. Lastly, let's look at this shape. I notice that there's no lines of symmetry for this shape, so that's just something to think about. And let's see if we could rotate this shape. If we would have to rotate it all the way around to be symmetrical. If I take this and I rotate it a little bit, if I rotate it just to here, it is symmetrical. Okay, and then I could rotate it some more, and it is symmetrical. And rotate it some more, and it is symmetrical. So this one definitely has rotational symmetry because I can turn it and have it on top of itself. Now we looked with the regular hexagon. Do you remember how many times you could turn it to have rotational symmetry? You could turn it 6 times and it would have rotational symmetry. Let's see if that is going to be the case with our regular polygons. Now you'll have to bear with me because it won't let me rotate around the center on this page. I don't know why. So you'll just have to use your imagination. Okay, we're going to look at this equilateral triangle right here. And we're going to look at 360 degrees. And let's see if this regular triangle would have rotational symmetry. And again, it won't let me rotate it around the center. I don't know why. But if I rotate this, where could I move this corner to? Would I have to move it all the way around in order to get this same shape? No, I can move this to 120. And again, it didn't rotate around the center. But if it rotated around the center, it would go right on this 120. And if I rotated it again, it's not rotating around the center, but if it did, then this green point would be right on 240. So this triangle has rotational symmetry if you rotate it 120 degrees or 240 degrees. It has rotational symmetry. Obviously, if you do 360 degrees, it's going to go back on itself. Okay, so there are 3 different rotations in the first 360 degrees. Now, obviously, you could do more than 360 degrees, keep going around and around. Let's look at a square and see what we can find out about this square. I'm going to put the 0 degrees on this corner here. And let's see. So here is the 0 degrees on this corner. A square is a regular polygon. That means it has all congruent sides. All right, let's see if this has rotational symmetry. We're going to look right here at this 0 degrees. At this corner, if I rotate it and if it moves perfectly around the center, which that one did pretty good, at 90 degrees, it would be the same shape. Okay, if I took that corner and moved it down here, 180 degrees, it would be the same shape. And at 270 degrees, it would be the same shape. So there's 4 different rotations up to 360. So at 90, at 180, and at 270 degrees, it is going to be back on itself if you rotate it. All right, what we want to do is think about what the rotational symmetry will be for any shape. So for example, the triangle had rotational symmetry at 120 and 240 degrees. The square had rotational symmetry at 90, 180, and 270. So let's see, for example, what an octagon would have without actually calculating it. How could we figure out how many degrees, if I started at this corner, how many degrees would it be to go to this first corner? Because obviously there's 8 corners, and if I drag those 8 corners around, it would be symmetrical. So how could I figure out how many degrees each of those corners is? The way you could do that is by taking 360 and dividing it by how many sides there are. Okay, so for example, and let me put 0 on one of the corners. For example, for this one, if there are 8 corners that we could rotate it onto, then that means we would be splitting this 360 degrees 8 different ways. So if we split that 8 different ways, you would just be dividing it by 8. So if we did 360 divided by 8, that is 45. What does 45 mean? What does 45 mean? That means every 45 degrees that you rotate a regular octagon, it is going to be symmetrical. So if I rotate it 45 degrees over and over and over, it is going to be symmetrical. So its degree of rotational symmetry is 45 degrees. Okay, and so in order to find the angle of rotational symmetry, you take this circle 360 degrees and divide it by the number of sides, which is like dividing it by the number of corners, basically, because that's what we looked at rotating. Let's do some example questions. A regular hexagon. A hexagon means there are 6 sides. A regular hexagon is rotated, and which rotation would result in a hexagon with the same coordinates as the original hexagon? Okay, again, a hexagon has 6 sides. So that means we would need to use the formula 360 degrees divided by the number of sides. And when we look at rotational symmetry, we always look at around the center, not around one of the vertices. Okay, if we rotate it around the vertice, which it probably won't let me do that, but if I tried to rotate it around this point, it's not going to be back on itself. Okay, so figure out which rotation would make it symmetrical. I would need to do 360 divided by 6. That means every 60 degrees, the hexagon would be rotated back onto itself. That's why it's 60 degrees. Which of the following cannot be mapped onto itself, which means rotated onto itself, by a rotation of less than 360 degrees? What do we call something that could be rotated onto itself with a rotation less than 360? That is called point symmetry or rotational symmetry. I've got an example of a square, trapezoid, regular hexagon, and regular pentagon. Which one of these do you think could not be mapped on itself in less than 360 degrees? So again, this won't let me rotate it from the center, unfortunately. But if I click and rotate a square, okay, I don't have to take it all the way around to make it look back like itself. So that means that a square can be mapped onto itself. This asks which cannot. So a square does have rotational symmetry. A trapezoid has 2 parallel sides. And if I click and rotate it, do I have to take it all the way around before it is back on top of itself? Yes, I do. So a trapezoid does not have rotational symmetry. You have to do 360 degrees before it's back on itself. Okay, a regular hexagon, we've looked at this already. It can be rotated onto itself before it goes all the way back around, and a regular pentagon can as well. So regular shapes are always going to have rotational symmetry. And of course, it's not rotating this around the center for some reason, but if it was rotating around the center, we would notice that there would be 5 different angles that we could rotate it that would put it back on itself. Which of these have point symmetry? All right, I could see this flower if I turned it so that this petal was on this petal, it would still look the same. So I would say that this does have rotational symmetry. This shape, I would need to take this point and rotate it all the way around 360 degrees before it looks exactly the same. So that does not have rotational symmetry. This heart, if I took this point right here, and I dragged it all the way around, it would not have rotational symmetry because it would have to go all the way around before it is congruent to itself. And number 4, let's see, if I took this right here and I moved it over to this right here, it would be congruent. You wouldn't be able to tell the difference, so you wouldn't have to go all the way around. So that means numbers 1 and 4 have point or rotational symmetry. Okay, what about these shapes? All right, if I clicked and rotated this in a circle, it would have to go all the way around. This would have to go all the way around before it's back on itself. So with this one, but D, I could rotate it so that this part is right here and it would look exactly the same. Okay, look at this figure and let's see. If the figure is rotated a certain number of degrees, the transformed figure will coincide, meaning it would be back on top of itself or mapped onto itself, with the original. Which of these cannot be the rotation? Okay, let's take a look at a negative rotation. Negative rotation is just going to mean counterclockwise. Anytime there's not a clockwise or counterclockwise, it's always going to mean clockwise. All right, so let's take a look at negative 240 degrees would mean going in the negative direction. All right, how many different times, let's think about how many ways we could rotate this figure for it to be on top of itself. If I took this petal and put it here, okay, that would be one way, or from here to here, or from here to here. So how many different ways do we need to divide up the 360 degrees? There's 6 different ways to turn it onto itself. So what we need to do is 360 divided by 6. That tells me that every 60 degrees it is going to be mapped back onto itself, every 60 degrees. Okay, so if we do 60 degrees, if I went all the way from this point to this point, that would be 120 degrees. If I went from this point all the way around to this point, how many degrees would that be? That would be 180. Okay, if I kept going from this point all the way around, that would be 240. If I started here and went all the way around to this point, and we're looking at dividing it in 6, then that would be 300 degrees. And then obviously 360 would be all the way around. Okay, so obviously 180 would make it mapped onto itself, so would 120, and this is saying which cannot. 320 would not map it onto itself. Negative 240 would mean we go backwards, go in the other direction, 240, that one would work. A windmill has 8 equally spaced blades. That's a tongue twister. It rotates clockwise, and it says how many degrees must blade P rotate to reach blade U? So it rotates clockwise, so we couldn't go backwards. We would have to go all the way around to U. To figure that out, first of all, we want to figure out how many times it can be rotated to get to U, how many times it could be symmetrical. To do that, we would want to take 360 and divide it by the number of sides. And what would that give us? We would need to do 360 divided by 8. So that tells me that every 45 degrees, that tells me that these blades are basically 45 degrees apart. Let's figure out how to go from P to U. How many degrees would that be? We would need to take 45 and multiply it by 1, 2, 3, 4, 5. So we would need to do 45 times 5. That tells me 225 degrees is the amount of degrees between P and U. Which of these letters has point symmetry? Remember, point is like rotational, but does not have line, means a reflection, same thing, line symmetry. So this means, which one could we pick up and rotate around the center and make it congruent, rotate it less than 360 degrees, but there is no line of symmetry? Okay, so these are our letters we have to choose from. Letter C, does this have rotational symmetry? In other words, can I rotate it less than 360 degrees and make it exactly the same? No, C does not have point symmetry. Does C have line symmetry? Yes, we could draw a line right here and it would be symmetrical. So that one's definitely not the answer because it's the opposite. Okay, the letter M. Does letter M have rotational symmetry? Meaning, can I rotate it less than one full turn around and make it look exactly the same? No. M does not have point symmetry, so it's not going to be M. Does M have a line of reflection? Yes, it does. It has a vertical line that you could reflect it around. Okay. What about O? Does O have rotational symmetry? Yes, it does. If we rotate it halfway around, it would be back on top of itself. Okay, so again, it's not rotating it from the center for me, but it would have rotational point symmetry. So this one does have point symmetry, but does not have line symmetry. Are there any lines of reflection in the letter O? Yes, there are lines of reflection in the letter O. That means O could not be the answer because although it does have point symmetry, it does not have line symmetry. And the letter Z. Does the letter Z have rotational symmetry? Yes, if I rotate it halfway around 180 degrees, it is exactly the same. Okay, so Z does have rotational symmetry, but does it have a line of reflection? No, there's no type of line that you could draw that would make it the same on both sides. So that's why the letter Z does have point symmetry, but not line symmetry. Okay, let's look at some more. The figure shows line segments A and B. This is a regular pentagon. The reason they drew these lines is because they're going to refer to them in the answer choices. Which statement describes a series of transformations that will result in a pentagon that is mapped onto itself, basically? Okay, rotating it 216 degrees clockwise about its center and reflecting it across segment A is one of the options. So first of all, before we calculate the degree of rotational symmetry, Let's figure out the lines of reflection. Does this regular pentagon have any lines of reflection? Yes. Is A or B a line of reflection? A is a line of reflection, but B is not. So let's keep that in mind. How do we find the degree of rotational symmetry for a pentagon? We would need to take 360 degrees and divide it by the number of sides. Okay, so 72 degrees is the degree of rotational symmetry. That means if I rotated it 72 degrees, it would be back on top of itself. Another 72 degrees, that would be 144 degrees, it is back on top of itself. Okay, another 72 degrees, that would be 216 degrees. So you could keep going and see what we get. So 216 degrees is a possibility. Now remember, to figure out if 216 degrees would map it onto itself, we could take this and just divide it by 72. And that would tell me that 3 turns of a pentagon would be 216 degrees. Okay, so if I take this 216 degrees, that would put it back onto itself. Then reflecting across segment A. Is A line of symmetry? Yes, it is. So if I rotated this across segment A, it would be symmetrical. Okay, so that's why that would work. This one says 72 degrees, and we know that 72 degrees is the degree of rotation. 72 degrees clockwise would rotate it onto itself, but B is not a line of symmetry, so that's why that would not be the answer. 185 degrees, if I divide that by the 72 degrees that I know is the degree of rotational symmetry, that is not even, so that tells me that 185 is not going to be it's not going to give us a congruent shape. And 144 degrees, that is 2 rotations. Okay, so that would take it back onto itself. However, B is not a line of symmetry, so that would not work.